Yes, I think, yeah, okay. So good morning, all of you. So if you look at it, right, the whole course, I think we will have probably 33, 34 lectures. And essentially there will be four sections to the course. Number one, the first part which we have already covered is, introduction to piezoelectrics, a little bit of history, and then how the material is kind of fabricated, and of course based on what physics, right, that we covered. We looked into the fundamental equations behind the material, and we also looked into how the equations are kind of represented to capture both the mechanical as well as the electrical properties. So that concluded the first part of our course. The second part of the course will be on ultrasonic sensing, which I kind of briefly touched upon in the last class. And it is how to say, a logical continuation of what we have been discussing on piezoelectric, because the fundamental principle behind ultrasonic sensing, or the material which we use in ultrasounds, ultrasound devices, is actually the piezoelectric material. So this is going to be the next part. So we kind of spent around 12 lectures to understand the piezoelectric material and the physics behind it, and of course the maths behind it. Now we will get on, and also we modeled, we also modeled the equation, the material with its electrical equivalent. And we solved, we also actually, by the way, we touched upon the applications a little bit. We looked into the oscillators. We spent quite some time on the oscillator, how the oscillators in actual electronic circuits, like for example, if you were to open your computer board, your laptop, or your mobile phone, right, you will actually see that crystal sitting in the board, right? So we discussed that, and then we briefly, I think we talked about, very briefly, we glanced through what all nice equipments can be made, right? Like the printer, the micro pump, or let's say, the resonator, right? Mechanical resonator. We looked into that, but the ultrasonic sensing is also, or ultrasound devices are also an application of the piezoelectric material. However, with this, we are going to take a deep dive into this topic, and we are going to look into the maths, the wave equations. We are going to, and what I have done compared to the previous, like if you look at the lectures of the previous years, you will see a lot of there is of course quite a bit of things which have I have kind of inherited what used to be covered in previous years lectures, but in addition, you will see in ultrasonic sensing especially, I will introduce you to the state of the art electronics, which companies are doing, right? And I actually used to work in the same group in Texas Instruments, which used to make this medical imaging chips, the parts which are actually the heart of the ultrasound devices. So I will show you, or I will walk you through the electronics portion of it in details, and that will be the pretty much the second, or maybe you can say the the third subsection of the piezoelectric portion. And then we will move in after the mid semesters. We will move into a completely different kind of topic. We'll look at feedback systems, and we will look at transducers, like in the domain of pressure sensing, flow sensing. We'll look at pneumatic transducers, hydraulic transducers. We'll derive the block diagrams and the transfer function, and see whatever things that you have learned in the control systems, right? We'll try to relate your learnings into the control system into actual equipments that are used. So that will be done after the mid semester, okay? So anyway, so let's proceed with ultrasonic sensing. And then so the next 6 classes, we will complete the piezoelectric part completely before heading into the mid-semester. And before the mid-semester, one assignment I've already given. I will give you one more assignment. And again, these assignments will not be textbookish assignments. You will have to use your, and that's the goal, right? I keep telling, I don't want you guys to mug up the subject. Even in the exams, you will find questions. I will not give you questions where you have to mug up the full equation. But however, you will need to remember, or you will need to know the relation of the final, performance parameter with the variables. That, of course, you will need to remember. But without more, so ultrasonic sensing, by the way, if you guys were to work for companies like Analog Devices, in India also, I don't think Analog Devices, they work on ultrasonic sensing in India, ADI, but you will see, the circuits that we will discuss in ultrasonic sensing, you will find them very relevant to many other domains of work, right? So, but before we go into the actual fun part, which to me is actually the circuits, the electronics of it, let us try to understand the physics and the maths behind it, right? So let's see. So what we use ultrasonic sensing for? We use this to detect the presence of objects, right? And I will clarify this a little bit more. We also use this to measure distance to objects, right? Track position or movement of objects, right? And each method of each of those above 3, right, uses a principle called ultrasonic time of flight. So for example, we know, right, all the modern day cars, right, if you're going for a relatively, relatively moderate relatively high-end car, right, not very high-end, we know that all these concepts of ADAS, right, I mean, few years back, 5 years back, we didn't even used to talk of ADAS, right, that was automated driver assistance systems, right. So things like ADAS is coming, and you will, if you look at the modern day cars, like, even Indian car manufacturers like the Tatas or the Mahindras, right? You will see ADAS is coming into picture. And of course, ADAS is there in the higher end cars for quite a few years now. Like Tesla's of the world has introduced ADAS, quite a few years back, right? But this is an active area of work and research, in the industry. If you were to join this industry, you will probably find yourself working in this. So in ADAS, one of the key things that is there is this ultrasonic, the ultrasonic based, sensing of objects, right? For example, if you are reversing the car, right, you will hear the car beep, beep, beep coming, right? In case there is a object at the back, right? So how it works is essentially using this ultrasonic sensing. It senses that there is an object and it will give you a beep, alerting you that you are going to hit the kind of object, right? So it essentially detects the presence of objects, it measures, and also it kind of sees how the object is, the position of the object is moving, right? And what is the basic method of measurement? So the basic method of measurement is by this principle called time of flight. For example, you send a sound wave, and that wave will get reflected back from the object. So if you were to measure the time that the sound wave, so let's say you give a pulse, a sound electric pulse, right, which creates the sound wave in the air. So that sound wave will propagate, it will hit the object and will be reflected, and it will come back to the same device, right? So if we were to measure the time difference between the wave propagating and coming back, right? And if we know the velocity of sound in the medium, then we can calculate what is the distance, right, of the object, right? So very simple principle. So this is how it works. So we have the transducer, it emits. So what you see, so please understand that, these diagrams are very innocent looking, innocuous looking diagrams, but it actually gives you a lot of message. So if you see, it gives a square pulse, right? So this is an electrical wave. Of course, the transducer is driven by an electronic system, right? So the electronic system gives, let's say, a chain of pulse, right, to the transducer. And the transducer, it's piezoelectric device, right? So we know if we give a electrical, if we apply an electric field, what happens to the piezoelectric device? It deforms, right? Or essentially, the other way to look at it is if we give electrical pulse, what will happen is the piezoelectric material will vibrate, right? Because it is deforming, it will, it will go back and forth between the shape, right? And that gives rise to, if the piezoelectric material is lying in a medium of, like, let's say, air, that vibration will create pulses, sound waves in the medium, right, in air. And those waves in the medium will be traveling. So if you see, so these are the waves that are created by the transducer, right? And then the waves travel, and the waves get reflected by the object, and the same transducer here, it is shown. I mean, we will see different transducer configurations when we discuss the electronics of it, but the same transducer measures, or it senses the waves getting back, right, after it gets reflected. And why this is possible, I mean, why piezoelectric becomes so relevant in this case, we have discussed this, right, that it can behave, it's a smart material, right? It has this reversible way of working. If we apply an electric pulse, it gives us a mechanical deformation, or conversely, if there is a mechanical deformation that can create an electric field across the transducer, right? That we have studied over the last 10, 12 classes. That's what we have looked into, right? So that same basic utility of the transducer of the piezoelectric material comes into picture here. Meaning, once the sound wave gets reflected back, what does it mean? It is actually creating pressure. It is putting a pressure on the piezoelectric material, and as the pressure keeps varying with time, because it's a wave, right? And we are going to look into the wave equations. Because it is varying with time, that means the electrical output that we will get from the transducer also will be like electrical signals. It may be in the form of a sine wave, right? So this is clear, right? Any questions that come to your mind at this point in time? Very simple way of, we'll take a very simple approach of understanding, and then we'll build the topic as we go along. Any questions that come to your mind? Okay. So what happens is, as I mentioned, that these waves, when they get reflected back from the object, it creates pressure on the piezoelectric crystal, and that pressure creates these electrical waves, which again is read by the electronics behind it. So whatever is sitting on this side, the electronics behind it, that also we are going to look into in great details. But this is the basic overall principle in which the ultrasound transducer works. It emits ultrasound energy. The energy it traverses forward in the form of sound waves. It gets reflected by the object, and the transducer, because it's a smart material, it works both ways. It detects the energy in the the waves that are hitting it, and it converts that energy into electrical pulses, right? So where do you think we may not be able to use these kind of transducers? Can we use these transducers everywhere? Or where do you think there will be a problem? We may not be able to use these. Anyone? Just take a guess. some comments from you guys. I'm looking for some comments. Take a shot, right? Where do you think we will not be able to use this kind of transducers? So the basic thing, if you see, right, is we need a medium, right, for the waves to propagate. We need a medium for the sound waves to without a medium. Can we use this transducer in space? Can we do that? Because space, as we know, is a great vacuum, right? So we will not be able to use these kind of devices where there is no medium of propagation of the wave. That should be clear, right? So this again is a snapshot of how the electrical signal is converted into a mechanical vibration. And this is very important, that we need a transmission medium. And there will be reflection, as we mentioned, and the reflected waves also traverse back, and then the mechanical vibration is converted back and read back by this electronic circuit sitting here, right? Okay. So from the name, we must ask this question that, sir, you are saying this is ultrasound, but what do we mean by ultrasound, right? And why is it called ultrasound? So essentially, this has got nothing to do, the name comes from nothing but the frequency of the sound wave that we are talking, right? So if you see, the spectrum, the sound frequency spectrum, right? So this is how we can categorize the broad spectrum of sound waves. So at very low frequency will be things like earthquake or volcano, right? So when there is an earthquake, it typically is in the order of few hertz, right? Very low frequency waves. These are and that creates very low frequency sound waves, right? And that is the reason why they say, right, that animals have a wider spectrum. I mean, they can receive the ear of the animals. So the ears, or even for human beings, those are nothing but filters. So that we will not discuss now. The human ear is also a C-type filter. It can be modeled as a filter. So the animal ears, they are designed such that they can pick up lower frequency sound waves, which we human beings cannot. We human beings, our typical audible range is somewhere from 20 hertz to 20. Human hearing is what, up to 20 kilohertz, right? So this is so from 20 hertz to 20 kilohertz, right? And then animal hearing, you can see, has a wider range, right? After that, beyond 20 kilohertz, is what we typically refer as ultrasound. And this again makes sense that we don't want to create sound waves in the when we are using our equipments, right? We don't want to create sound waves which human beings can hear, right? Because then we'll all go mad, right? If let's say all the cars going around, each of the cars, their transducers are emitting sound waves in the audible range, then we will go mad, right? In this audible range of 20 hertz to 20 kilohertz, then that will be bad, right? So we need to operate in a zone which is not going to create problem in our day-to-day kind of behavior, right? Or day-to-day kind of activities. So the reason why it is called ultrasound is because if you look at the frequency of the waves are beyond 20 kilohertz, and it can stretch all the way up to 200 megahertz or so. And then there are, even in this spectrum, there are different zones. Like for example, just beyond 20 kilohertz, you have this automotive parking assist. Then, things like water level sensing or liquid identification, what kind of liquid it is, right? Then somewhere in the megahertz range, 2 megahertz, somewhere maybe around 10 megahertz or so, we have this medical diagnostics. Then this is for industrial testing, and then this is for medical imaging, acoustic microscopy, right? So this is so basically there is a wide range of frequencies of ultrasound which are used. So application wise, in terms of whatever application it is going to be used for, the frequency of operation will depend on that, right? So another basic thing for our transducer is the transducer frequency and size affects few things, right? The detectable range, right? The size of the material and the frequency in which we are operating that will affect very important parameters. The detectable range, right? How far the object is, right? For example, let's say you go to a hill station and you are, emitting a sound wave using your, handheld transducer, and you want to kind of measure the distance of the nearby mountains, right? You may not be able to do that if the size of the transducer is too small, or essentially what happens is the intensity of the sound waves that the transducer is going to emit is not going to be large enough to reach and hit the mountain close by and come back, right? So essentially the intensity of the waves or the power content in the waves should be such that it should be able to go that far and then come back, right? Because there will be loss in the medium as the sound waves propagate. There will be loss, and we are going to quantify each of these, the power, the sound wave velocity, and all that in the mathematics portion when we deal with it. But it kind of makes obvious sense that if the transducer size is small, it may not be able to detect objects far from it, right? Or also the field of view, right? If it's a very small kind of cross-sectional area, it will be transmitting waves only maybe in one direction, right? It may not be able to see an object, which is sitting at a very steep angle compared to the transducer. This also makes sense, right? And of course, accuracy. We are going to look into this also in great details, what we mean by accuracy, right? So this kind of makes sense, right? I'm just trying to set the basic physical parameters first before we go into the maths. Any questions up to this point, guys? Okay, and so these are the modern day applications. I talked about ADAS, right? The parking assist system. So if you look at the warehouses of these large companies like Amazon or Flipkart, right, where they have huge amount of consumable items stacked up in a big space, right? You will see much of the movement of the items happen by using this robotic kind of machines, right? So these robots will move such that there will be no collision with each other, right? So essentially they need to detect that, okay, I'm not, it's like you have to give some eye, right? You have to give an eye to the robot, right? So these kind of collision avoidance system in robots, specifically used in these warehouse kind of applications, right? Use this kind of ultrasonic technology. Actually, the last part that I was designing, I was designing an ADC for TI that is going to be released in the market. So that ADC is actually sitting in exactly this kind of a system. We'll not talk about ADCs in this course. It's outside the scope of this course, but so this is where ultrasound can be used. And of course, the drones, you can easily figure out why it should be using ultrasound as sensing, because the drones keep measuring the distance, right? How far it is from the ground, right? So it needs to measure the distance, right? And similarly, object counting and detection. So all these are applications where you'll get to see ultrasonic transducer. The advantages and disadvantages. So the advantages of ultrasonic transducer, it's actually waterproof, enclosure resistant. We can actually put a waterproof enclosure around the transducer and make it resistant to moisture and rain. And that kind of is understood, right? That because we are relying on sound waves, the sound waves can propagate through thin barriers, right? Of course, if you put a thick wall, then it will not be able to kind of propagate. But then through thin barriers, we can essentially design the product such that it can be enclosed in a very safe kind of environment and can be used for variety of applications, especially where rough weather or where you have moisture, rain, these kind of stuffs, right? It can be used for wide variety of environment. It is pretty robust. Dirt and dust. The environment need not be super clean for these transducers to work effectively. Wide temperature range of operation. This is very important. Wide temperature range. We'll talk about this in the electronics portion. Ability to detect opaque and transparent objects, right? So the advantage of this, for example, is because, so let's say if we have mirror, right? If we have a mirror and if we are detecting an object which actually does not, so a mirror means what? If we throw a light ray to a mirror, right? Not mirror, let's say a glass, piece of glass, not mirror. Mirror will reflect the light ray, but let's say we have something like a glass object, right? The light ray will pass and much of it will not be reflected back, right? But here, because we are relying on sound, the reflection will actually happen. So even for transparent objects, we can use ultrasound to detect the presence of transparent material or transparent object, right? Okay. What are the disadvantages? Inability to detect objects with similar acoustic impedance to transmission medium. So this is very important, very, very important, and we are going to talk about acoustic impedance, right? So what that means is, let's say we are emitting a sound wave, right, and it is propagating through a medium. Let's say it's propagating through air, and then it is actually hitting so a material which actually has similar impedance. Now, what is impedance? Again, hold on to the horses. We'll come back to that. But the point is just like the example of the glass, right? The transparent glass, where the glass does not reflect, a transparent glass does not reflect the light ray back, right? It actually transmits it to the so this reflection coefficient of a mirror is very low, right? Most of the light ray will pass through the medium, right? So similarly, if the material that we are trying to detect, it has an acoustic impedance very similar to air, then it is not going to reflect the sound wave back, right? And it will be absorbed. So so this is one disadvantage, and of course, because it is ultrasonic, it, as we mentioned, it cannot be used in vacuum, right? So far so good, right? It's just general description. We are trying to understand where all we can end up using this kind of a transducer. So now we have to get into the maths portion. So as a build up to that, so how do we kind of study ultrasound, right? What are the basic physical parameters associated with ultrasound, right? So it can be quantified in terms of oscillation in pressure because we are talking of sound, right? So these are like pressure waves propagating through air or through a medium, right? It can be water as well, or it can be blood, or so in medical processes, the sound waves propagate through the human body, right? So it propagates through a fluid, can be air or, as I said, water or blood or whatever. But what that propagation means is, how does it propagate? It creates a pressure wave or stress, which also means that as the wave is propagating, the particles in the medium will be displaced, right? Only then there will be a propagation, right? That the particles in the medium will have to move. Only then, if the particles are not moving, not doing anything, then there will be no movement, right? Particle velocity, right, in the medium, and of course the characteristics of the medium itself, which is the wave, which is going to define the wave motion. So it is very important. As I said, we are going to get quite deep into physics after this and look into equations which might sound pretty boring for you people, But my job is to make it interesting, and more importantly, you should understand that, because without understanding the physics or the maths behind it, it is impossible to develop the electronics. So we must understand the physics before we go on to develop the electronics. Okay. So basically, we are going to study ultrasound in terms of pressure, the particle displacement, the particle velocity, and the characteristics of the medium in which the wave is going to propagate. So far, so good, right? No problem, right? Anything that comes to your mind, or anything you feel that there's a disconnect in what we have been discussing so far and where we are heading to. There is no disconnect so far, right? Piezoelectric to the ultrasound, and before going into the electronics of ultrasound, we have to study the characteristics of the waves, right? Okay, so now that brings us to the nature of waves, right? So we will talk of waves in, like, we'll categorize waves in two categories: longitudinal waves and transverse waves, right? And we'll define how each wave looks like, right? So if you look at the first picture here, picture on the top here. So this is a medium. Let's say you are in a room, right? Nobody's talking, everybody is silent. Then the air particles are kind of, we can say, they are almost like, we can treat them as stationary. Nothing is kind of moving, right? Nothing is happening. So these are the particles at rest. It can be air, it can be water, it can be blood. So essentially it is to show that, so these are, let's say, the particles, all of them are kind of stationary, right? The gaps between them are kind of consistent, right? There are no, it's kind of equally spaced, right? Now, when a longitudinal wave propagates, right? So if you look at the second category here, when the longitudinal wave propagates, so the direction of the wave is, of course, from left to right. We have denoted the movement from left to right, right? And if the wave is propagating from left to right, the direction of the particle motion, in the case of a longitudinal wave, will be the same, or it will be parallel to the motion of the wave itself. For example, if you see the distance of the particles here in the steady state condition without any wave, where these are all equidistant, right, or equally spaced, right? But as the wave is moving from left to right, what we see is few particles have gathered close to each other, and in few other places, and this is space. This is space, guys. Okay, the x-axis in this is space. It is not time or anything else, right? It is the three-dimensional space in which we are sitting, right? So some of the particles in a certain position of x are kind of close to each other, and in many other places the particles are far away from each other, right? So this is how the longitudinal wave will look like. It is going to move from the left of our screen to the right of the screen, and as we can see, the particle movement also happens in the same direction, right? It vibrates. So the position of the particle, still the mean position remains the same, but the particle will vibrate in the x direction around the mean position, right? So this is how we will define as longitudinal wave. And then there are transverse waves, which, of course, if it is longitudinal, the transverse waves also can be understood. That instead of, so the wave is propagating in, from the left of the screen to the right of the screen. But in the case of a transverse wave, as we see, the particles are moving perpendicular to the motion of the wave, perpendicular to the motion of the wave, right? So the particle has moved, so few particles have moved far apart, far from the stationary position of x, right? It has moved up, few particles have moved down. So the movement is perpendicular. So this is how we define transverse waves, right? So this is clear. Any question that comes to your mind, please feel free to ask questions, because without that, I feel that, there is, I'm not able to communicate with you guys properly. Any questions that come to your mind? Okay. So the particles of the medium only transport the vibration of the ultrasonic wave, but do not travel with the wave. So this is very important to note. that while the wave energy is traveling across space, right, it is traveling from the left side of the screen to the right side of the screen, the particles are moving, but that does not mean that the particle itself is actually moving, meaning, so let's say a particle is sitting here, it doesn't mean that this particle is going to move along with the wave in the x direction. So that is not what is actually happening, right? So that is one thing. The second is the medium can cause waves to be reflected and refracted or attenuated over time. And this happens again because the movement of the particles itself will be restricted, right? Or it will, the movement will happen in such a way that, the waves will not move forward. It will be completely reflected, or some portion of it is reflected and some portion of it is transmitted, right? So again, because we are talking of velocity and of sound and all that, so from your basic class 11-12 physics, you must know that the propagation is affected by density of the medium, the pressure, let's say in this case if it's atmosphere, the pressure, the air pressure, the temperature, the motion of the transmission medium itself, meaning if there is wind, let's say, right? So the air as a medium itself is moving, right? Or let's say even if it's water, right? If the water or a fluid, right? If the fluid itself is moving, right? The motion itself will affect the speed, right? That again from basic class 11-12 physics, and of course the medium viscosity. If it's a like thick fluid versus, or I mean thick is a layman's term, but what we mean by a thick fluid is a fluid which is viscous, whereas a fluid which is, let's say, not as much viscous, right? The velocity is going to be dependent on the viscosity of the medium, right? And here on this graph, what I have shown is this is, let's say, the altitude. Let's say this is our sea level and this is the altitude. And then what we have shown is how the, if we look at, the density is plotted from, let's say, on this axis, the yellow curve, the density is plotted on this axis, and the temperature is, of course, in Kelvin, right? So if we plot the altitude and the temperature, or these kind of parameters, if we plot the sound wave, we'll see how the the velocity is kind of varying with respect to the altitude or the density or the pressure or the the speed of the sound is of course denoted by this guy, how it varies with temperature. So if you see the temperature in actual space is, let's say, varying like this, then we see the speed of the sound wave is also kind of dependent on temperature, right? It closely follows that, right? So again, because it's a wave, we are going to talk of wave in terms of frequency, the wavelength, the amplitude. So essentially, it's the same stuff. If you see from our electrical, when we talk of a voltage, sinusoidal voltage, right? We talk of the frequency of the voltage waveform, the period. Period and frequency are kind of like related to each other. It's one and the same thing. The amplitude or intensity, the direction or speed, right? The velocity vector, and the wave number. So this we are going to talk of what is a wave number. So all these properties we will kind of look at to describe a particular wave. Okay, so now we are going to get into the wave equation, and this is going to be a little bit involved. So I want you guys to be attentive and catch hold of me if you can ask questions if something flies above your head, right? Because this is going to be physics. So generally, ultrasound transmission in homogeneous medium is represented by a plane wave, right? Plane wave propagation, which we talked about. In many applications like ultrasound imaging of human body or composite materials, the plane wave approximation is not valid, right? In such cases, we will represent it by a scattering medium with absorption, right? So just like I said that not the complete wave not all of it will be propagating in from one direction to the other. If it hits an object, some portion of it will be reflected and some portion of it will be transmitted. So we are going to look into that relation also. Okay. So let's say we have a piece of the medium. So let's say it can be a piece of fluid or it can be air or whatever. But let's say we are representing that medium as a as a cube, right? And so this is very important, guys, because next few slides are going to be heavy mathematics. So bear with me. And as I said, catch hold of me if you are not understanding. So let's say, so this is a piece of fluid. We have assumed this to be a cubic kind of geometrical shape. And we have assumed this just to make the maths simple, right? Or we have to come up with a framework of doing the maths, right? So let's say on this edge of the fluid, the velocity of the particle, this is very important, the velocity of the particle we are denoting as ux. U is the velocity and x is a function of the x-axis. So this is my x-axis. So u is a function of x. And on the other edge of this cubicle, of this cube that we have drawn, right, the velocity is x plus delta x. So basically, let's say this is my x coordinate and this is my x plus delta x coordinate, right? So the velocity as the wave is propagating, right, the particle velocity at a coordinate x is u, and the particle velocity at a coordinate x plus delta x is a function of that coordinate x plus delta x, right? Similarly, the pressure on this side of the cube is, let's say, px, and the pressure on the other side of the cube, please note the arrows are in opposite direction, please note that, right, is x plus delta x, right? P x plus delta x is a function of space. That's all what we are communicating. This picture, that's all what it says, right? And this cube has an area. The face of this cube has an area A. Okay. So then, what is the total mass of this piece of fluid that we have? That will be nothing but the density. What is the volume of this cube? If this area is A, and this is actually delta x, right? Even though I'm representing this as a cube, but let's say this is x and this is x plus delta x, right? So what is the volume of this cube? It is this area A multiplied by delta x. This is my volume. Volume multiplied by density is my mass, right? No big deal. So now, what is the force associated, with this piece of material or this piece of fluid, right? So we know from Newton's law that force is mass into acceleration, right? And which is m into m multiplied by du dt, right? And this du dt, u itself, what we have done is a function of x, right? So what we have broken this du dt into two components, a time varying component and a component varying with x, right? Any problems with that? So then, but del u del x itself, so if I rewrite this equation, right? So del x del t itself is nothing but u. Del x del t is nothing but the velocity of the particle. So I'm writing the force as mass multiplied by del u del t multiplied by the velocity and the change in velocity as a function x itself, right? So, and what is this force acting on this material, on this cube? We have a pressure Px applied on this direction and Px plus delta x in this direction, right? So the force in this direction is Px minus Px plus delta x multiplied by A. That's the force, right? Because this is my area. Any questions? And this I'm equating to this mass we know, This mass comes from here, right? So this is what I can represent it like this, right? Any problems, guys, with this? Okay. So if there are no problems with this, then the next step is as delta x tends to 0, right? So as delta, I can bring this delta x here downstairs here. As delta x tends to 0, so this portion I can represent is at del p del x, right? The area is of course non-zero, so I can cancel this out. It's not 0, so it's safe to cancel them out. So del p del x minus, why it is minus? Because del x I'm taking in this direction, right? In the positive direction of x, and it is px minus px of x plus delta x, right? So it is minus del p del x. The change in pressure, the negative or the inverse, I shouldn't say inverse. So the negative pressure gradient as a function of x, right? That equals rho, which is the density of the material, multiplied by del u del t plus u del u del x. Clear, right? I've just taken, I've just approximated del x to be a very small quantity, and whatever equation I wrote here, I just, to give it a form of calculus, I'm representing the portion on the left hand side as del p del x, right? So, and what we will assume for now is the velocity does not change with x. Or even if it changes, it's very small. So this component we are going to neglect for now. Del u del x is approximately 0. We'll assume this for now and proceed. So then if I can write, so if this is 0, right, I'm just rearranging this term and this term, and I come up with the first fundamental equation, that del p del x plus rho times del u del t equal to 0. Right? Any questions up to this point? We are going to keep this equation safely, and we are going to revisit this later when we are deriving the further steps. Is the math getting too boring, or you are understanding, right? Am I able to explain why the equations are looking like this? Because that is the key, guys. And I keep saying, right, no need to mug up, but can you understand why the equation is looking like this? I actually referred to multiple textbooks and material, and then in many places I was not convinced with the derivation, and much of this derivation that you will see is actually done by me myself. In the following slides also you will see much of the derivations are done by me to ensure that there is continuity in the understanding. Any questions up to this point? Also, what we will assume is, because it's fluid, right, and because the particles themselves are moving, right, that we saw in the previous, for the longitudinal motion, we saw that the particle in some places are getting close to each other, and in some places it is getting far from each other, right? We saw that in the previous slide. So that means the density is also a function of time, right? So what we can write this rho, meaning the density, we can write this as two components. One which will be a fixed component, which is actually the density of the fluid, and one is a time varying component, right? And again, it is safe to assume that the wave motion is such that the time varying component of the density is much smaller than the absolute mean density, meaning the variation, there will be variation in. So what does this equation tell us? It tells us that, look, the density will be varying with time, but the variation, the absolute amount of the variation will not be much. It will vary, but it is a function of time, but it will not vary from the mean, because if it varies from the mean, then all our assumptions of the equations that we are going to derive is going to, so basically you can think like this, right? The ADAS or the transducer sitting in your car, right? It will give you a sound wave, but if the wave intensity is such that it is creating a storm around your car, that is meaningless, right? So basically, it creates particle movement, all right, but not to an extent that the density is going to change significantly. Okay. So now if we replace this guy in this equation, we land up with this, right? We are going to keep this equation with us. Any questions up to this point, guys? Because the next few slides I keep saying these equations, we're going to keep falling back on these equations. Okay, so now let's look at what is the mass change in the volume, right? Meaning in the previous slide, so this is the volume that we have considered, right? And because it's a fluid and because the wave is propagating, we discussed that there is a change in density. But what it also means that because the particles are kind of moving from their mean position, right? So there is little bit of the mass content in this cube, in this little cube, that mass will keep varying with time, right? What is the mass change in volume? So A is the area of that cube that we have. It's not cube, area of the piece that we have assumed, and delta x. So this is the volume, right? So this is the volume, right? And what is the mass flowing out of that volume? Is the volume multiplied by the change in the density, del rho del T. Is that clear? And why is this minus sign there? The reason why this minus sign is there, because if you go back to the previous slide, right? The reason why this minus sign is here, because we have assumed x plus delta x, the pressure in this is px plus delta x, right? So the pressure gradient is opposite to the x gradient, right? So because of that, the mass change in the volume is the volume multiplied by the change in the density as a function of time, right? Also, I can represent the same change, same mass change in volume, not only by this, but also by this. And how is that possible? So this is the density at x plus delta x. This is the velocity of the particle at x plus delta x. And this, so this is velocity and this is density. So velocity multiplied by area, if you do the math, right, if you understand velocity multiplied by area, it gives rise to the volume and the time. So this del T component comes from U, right? Right? So the change in the mass can also be written like this. No confusion in this, right? Any problem? And here there is no minus sign because I am moving along the x gradient, right? I'm moving along x-axis. So the mass change in the volume is this, as well as I can represent it like this, right? Any problem? Then that means I can equate this, right? If I equate this and then again go back to my limits, I take del x equals 0, I bring this guy downstairs here, right? So this portion I can represent as del rho multiplied by u del x. And then this guy minus del rho del t, this I have brought on this side. I'm just rearranging this equation and I come up with this. And hold on to your horses, as I said. I mean, what does all this signify? You will see the significance. Everything will converge into nice electrical equations or electrical equivalent models. So is this clear? Any question up to this point? Okay, so for today we will stop here, and then I will request you guys to whatever I have discussed, right? Just look at the equations and then see if anything that I have derived is not understandable, or you feel that I have skipped a step, or my assumptions, the assumptions that I'm making in the equations, those are incorrect. Please feel free to go through that and ask me questions, because as I said, while most of it you'll probably find in different textbooks, or but the absolute derivation is actually done by me. So please go through it and raise your hand if you're not able to understand. Okay, so thank you then, guys, and I'll stop the recording and have a good day. We'll meet tomorrow.